Welcome back, everybody. Today we are going to be working on question 8 of the Winter 22 midterm exam. So this question presents to us a new ISA, and we are asked to kind of familiarize ourselves with the new ISA as well as learn how to work with it. So the main idea of this ISA is that we're going to minimize the number of registers that we have. In particular, we have a buffer register, which allows us to move register values to and from memory using load buff and store buff. And so it's very similar in that sense to like the data register. And then we can move values between different registers via the instructions load reg and store reg. The RZR is just a register that always stores 0. And then we have two like relatively normal LC2K registers, which are just our primary register and our secondary register. And then it gives us a bunch of instructions. Okay, so part A is asking us to, if the instruction is encoded in 16 bits and the addresses in load buff and store buff instructions are unsigned immediates, what's the maximum number of address bits that can be in this ISA? So let's look at the load buff and store buff instructions. So those are these instructions right here. And the only things that are specified in them is we're going to have some number of bits, right, associated with telling us which opcode to choose, right, telling us that it's load buff or store buff. And then we're going to have an immediate value. The question is asking us, how long can those immediate values be? So because we know that the only other thing in these in these instructions is going to be the opcode, it's going to be the number of bits that we can use to represent it is going to be 16, the total instruction length, minus the number of opcode bits. Well, how do I know the number of opcode bits? Well, I need to consider how many instructions I'm representing. So if we look at our table, I count 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 opcodes. So what's the minimum number of bits used to represent 9 opcodes? Well, it's going to be the ceiling of the log of the number of opcodes. So in this case, it's 9. And so the value that we're going to get here is 4. So we have 4 opcode bits. And the rest of the instruction can be used to represent the address, right? And so 16 minus 4 is going to give us 12. So there's going to be 12 address bits in this instruction. The second part of the question asks us the highest loadable or storable address. Well, essentially, the first question that we can kind of answer that's kind of indirectly asking is how many addresses can I store in 12 bits? Well, I can store 2 to the 12 bits, right? Or 2 to the 12 addresses. And so that means if I do the math in my head, it'll be 4 times 2 to the 10, which is 4,096. This tells me that there's 4,096 addressable positions, right? What it doesn't say, but what the question is not asking me how many different representations there are, it's asking me what's the highest storable address, right? And because like 0 is a valid address, essentially like what's 1, 1, 1, 1, 1, 1, 1, 1, 12 ones going to represent? Well, that's going to be 2 to the 12th minus 1, right? Which is 4,096 minus 1, which is 4,095. So that's going to be the highest address that we can reference, excuse me, in this instruction. All right. So part B says, use the new ISA to implement the C pseudocode on the left. Solutions exist that don't use all lines. The variable mem is an array of 32-bit values. Okay, awesome. So this instruction asks me to perform check if mem at address 8 ANDed with 1 is true, right? If that's I guess it would be a 1 or a 0. If that's a 1, then we want to branch to the label goal. If that's 0, we don't want to. So let's try and do this. So the hint that it gives us is how do we perform, because we don't have like an AND instruction, right? We have NAND I and NAND. Because we don't have an AND instruction, how can we make it, right? Well, we can take, if we wanted to AND A and B, we can NAND them with each other, and then we can NAND the result of that with itself, right? Essentially, this is kind of like a NOT, and this is a NAND. Awesome. So let's consider what we're doing. So the line that it gives us at the very start is it says load buff 8. What this does is it says that buffer is equal to mem at location, at location 8. Then it says load reg RPR. So what that does is it says RPR is equal to buffer. So essentially, what we have is RPR is equal to mem at location 8. So in these next couple lines, what we probably want to do is perform the bitwise NAND. So, the bitwise AND. And so the way we do that, we can kind of take, I'm going to walk you through 2 solutions, right? So the first solution is using kind of our hint, which is we want to perform the NAND between mem at 8, which is currently located in RPR, and 1. So it tells us essentially first what we need to do is a NAND between the value 1 and mem at 8. And, well, if I wanted to perform a NAND, essentially I want to perform a NAND I, right? Because I want to NAND an immediate value of 1 with the RPR, right? And so I can go ahead and do that by performing NAND. So what we can do is RPR is equal to RPR NAND 1. And we do that by doing NAND I 1. So that gives us kind of like this output right here. So now we want to NAND that with itself. So how do we perform essentially RPR NAND RPR? Well, if we look at our instructions, we don't have an RPR NAND RPR. What we do have, though, is we have RPR NAND RSC. So essentially, if I set RSC equal to RPR and then I NANDed them together, I could achieve the same effect. Well, I look at my instructions again and I say, well, I don't have RPR equal to RSC. However, there is a tricky way we can do this, which is we can set the buffer equal to RPR. So I'm going to write this. So you can say buffer is equal to RPR. And then we can say RSC is equal to buffer. And then once we've done that, so RPR is now equal to RSC, we can, calculate RPR is equal to RPR NAND RSC. And the value that we'll get then is our output, which is mem 8 and 1. So how do I set buffer to RPR? Well, I think that was store reg, right? So we can do store reg RPR. And then to set RSC to the buffer, we can do load reg RSC. And then if I want to NAND them together, I believe we just perform NAND, right? No arguments there. And as a result, what we've successfully done is mem at 8 and 1 now exists at RPR. Oh, geez, this Apple Pencil is really messing with me. Jeez. Okay. So now I want to perform a conditional statement, right? I only want to branch to label goal if RPR is equal to 1, right? It can't be more than 1 forming a bitwise AND, but yeah. So it gives us some pseudocode here. It says store reg RZR. So what that's doing is it's saying buffer is equal to RZR, which is always going to be 0. So it says buffer is equal to 0. So just kind of thinking about this, how could we check if our RPR is going to be one of two values? It's going to be 1 or a 0. So if instead of performing checking if it's equal to 1, what if we checked if RPR was equal to 0? If it's equal to 0, we could jump to end. And if it was equal to 1, then we could jump or perform BQ goal, right? So let's see. Well, how does BQ work? Well, BQ branches if RPR is equal to RSC. Well, RPR is already the value that we want, right? We already have that as mem 8 and 1. And so to compare it to 0, we could just set RSC, because buffer is 0, we can set it RSC is equal to buffer. And so the way we do this is same as earlier. We do load reg RSC. Awesome. So then it says if 0 is so if Jesus if 0 or sorry if RPR is equal to RSC, then jump to or branch to end. Otherwise, we're going to execute this other statement, right? And to do that, I want this jump to be unconditional. No matter what, I want to jump to goal. And as such, there's a couple things I want to do. I just need to guarantee that RPR is equal to RSC. And I need to do that in one line. Well, I know that RSC is equal to the buffer, which is 0. So one option that comes to mind is we could just do load reg RPR. And what that does, it says RPR is equal to buffer. And because, if I change colors for a second here, because, here, oh, geez. Because, I'm just going to go ahead and undo that. So we'll take a second. So we said load reg RPR. The idea is because RSC is equal to buffer and now RPR is equal to buffer, they must equal each other, which will guarantee that last branch. So that's one solution for this question. There actually is another solution. And so I'm going to really quickly delete this. Oh, geez. Okay, so the other solution, so we're still going to perform NANDI1 here, which gives us this output, right? But instead of using like the hint that we provided here, which is you can NAND something with itself, the other way is, and this is a little bit of a trick, is we could NAND something with all ones. Well, how do we represent something with all ones? Well, that's in 2's complement, -1, right? So essentially, we want to say that RPR is equal to RPR and like NAND one, -1. Geez, it won't let me write on the edge there. And so the way we can do that is NAND I -1. And that will give us the same value, the same output for Q, or the same mem 8 and 1 is now stored in RPR. It's a little bit tricky, but if you came up with that solution, good job. It's quite a tricky one. So then we still store 0, and we still can do a load reg RSC there, right, which sets RSC to 0, and then we compare and check. And so the other way to, so essentially we want to set RPR here to 0. And so another way to set RPR to 0 is because you know that RPR is currently 1. If we subtract 1 from RPR, if we subtract 1 from RPR, then we can guarantee that they're the same. So the other option here is going to be an add I -1, which essentially says RPR, can't write RPR, it's very confusing, is equal to RPR -1. And because we know that RPR is currently 1, because it must be that value to get here, it'll just say RPR is equal to 0. It's essentially the same thing. But those are 2 potential changes that you could make to your solution. And I believe we accepted both of those. Okay. So that's part B. For part C, it asks us to do something similar. So I'm going to switch colors because I'm sick of seeing blue. Let's do this thing. Okay. So load buff 64 says that buffer is equal to mem at 64, and then RPR is equal to buffer. Okay. So okay. So now, so essentially what that does is currently mem 64 is inside RPR. So the first thing that I would maybe want to do is add 3, right? I want to add 3 to my RPR, right? And so the way I do that is add I. Add I 3. So what that does is says RPR is equal to RPR plus 3. Awesome. So now that we've performed that, I want to left shift, right? So a left shift by 2 is the equivalent of multiplying by 4, right? Because if I bit shifted by 1, that's the equivalent of multiplying by 2. If I'm bit shifting by 2, I'm multiplying by 4, or I'm multiplying twice. So let's look at how we can do that in our current way, right? So I have 2 options. So one way I could do it is if I want to multiply, if I want to double something, I'm going to need to use RSC, right? I'm going to either perform, I'm going to need to perform add instructions, right? So one way is I can add I can set RSC to RPR, right? And then I can add it to itself 4 times, right? Or add 3 times of itself back, right? So we can do that first. I think this is the solution that I did when I was taking this the first time. But so remember, the way we can do RPR is equal to RSC is we can set buffer is equal to RPR. Geez, can't do this. RPR, and then we can say RSC is equal to buffer. And the instructions that we use then is store reg, RPR, and then load reg, RSC. So now RSC is equal to RPR. So now what I could do is I could say that, excuse me, RPR is equal to RPR plus RSC, right? And we could do that 3 times, right? And the way we do that is we just say add, right? So essentially we're multiplying by 4 by adding 4 copies of RPR to itself. So that's one way of doing it. The other way is instead of calculating essentially, if I was trying to multiply 4 times A, instead what we did there is essentially we did A plus A plus A plus A, right? One way I could do it is, the alternative way I could do it is A plus A is equal to B, and then I could calculate B plus B is equal to like our final answer. Is technically 4A. And so what we have now in RPR is essentially 2 times mem at 64 plus 3, right? We have 2 times A. So essentially we could do the same thing one more time. We could do store reg RPR and then load reg RSC. So what that does is it says essentially turns it's kind of like assigning B to 2 times A, right? And then we just perform another add, and that will give us the same solution. So 2 different ways of going about that question, both perfectly viable. That took quite a bit of time, but that was all I have for question 8. Hopefully you find that helpful. I'll see you all, or hopefully all on number 9.